Is energetic efficiency of resource state generation for fusion-based quantum computation. Very catchy title, I have to say.
Thank you. Yeah.
Okay.
Thank you very much for the introduction. So it is a very specific title, the energetic efficiency of resource state generation for fusion-based quantum computing. It's a very niche subject, but actually I'm kind of happy to be near the end of the conference because there's a lot of building blocks that have already been discussed. So I want you to think back of the photonic architecture that Ariane presented this morning, the error correction that Michael presented this morning, and like the slew of metric noise resource efficiencies. Before I begin, this project, I'm just a humble messenger today. This project is ongoing with a number of people in Singapore. Harshit and Ariane are here today, as well as Quandela. So this is one of the BAC and OECQ flagship projects. Right, so how did this project come about? I don't think everyone here is an expert in photonics. Photons are really nice because we can make many, many of them. But in linear quantum computing, or in quantum computing with linear optics, they're really hard to entangle. So everything is kind of probabilistic. We don't have any deterministic operations. And so to combat this, fault tolerance relies on the generation of resource states with a lot of built-in redundancy. And any circuit that you do, you want to optimize you want to minimize the depth just to fight off natural photon loss. And so in 2025, Quandela looked at the efficiency of making what's called a resource state for fault-tolerant quantum computing. I'll get into what this resource state is soon. And they looked at just different architectures and how they scale, or how they would scale if we could do quantum computing. And at the bottom, there's some more mature architectures basically relying on creating entanglement before the photons really exist, like basically minimizing future entangling operations. This is very nice, but if we remember all of the Tuesday talks about a full stack efficiency, this is optimizing over a single stack. So we're not considering the microscopic nor the macroscopic, we're just looking at a single layer. So what we did, we wanted to start this project by taking what they had in one, or in this first paper, this first look draft by Quandela, and then extending it to this full stack regime, where we're going from the ground up, we're opening the black box of photon sources, and we're looking at the efficiency from a logical error, or FBQC metric. Ariane flashed this photo this morning. This is the Quandela setup. It's a deterministic photon source that emits about 10 to the 9 photons per second. And there's this universal interferometer. There is, of course, noise, the distinguishability, which basically means that photons, the quantum effects that you want, won't happen, and you have loss through the interferometer itself. And so what we do in this project is we're not going to consider the full stack, but it's mostly a full stack. We're just going to look at the energetics from a fault-tolerant regime. And so we'll look at the cryogenic load as the main resource cost. This is going to be the most energetically expensive. And what we want to optimize is the logical error rate, such that we can actually do some sort of computation. We'll play with optical loss and distinguishability as noise, and we can tune different hardware parameters and specs, the code distance, and the number of photons that we're actually emitting. And so MNR has been discussed at length. Just to remind you, this is a difficult optimization task because whenever you tune one of these dials, you're going to inevitably tune the other ones. To give a good idea of what we're optimizing, for fusion-based quantum computing, we have this stabilizer. It's called lattice stitching, the formalism that we're working in. It's not so crucial. Just know that we need a lot of these resource states in a grid, and generally, you need to be within some sort of threshold region, and we want to hit some sort of target metric. And there are known scaling laws that say that your logical error rate scales like the physical error rate over some threshold to the exponent scaling with your code distance. So say I want to hit a target of 10 to the minus 12. This is called a teraquap. It's, I think, established through classical metrics. I can do two things. I can either, to suppress logical error rate, I can either increase the code size, and this is going to increase the resource state overhead. These are purely qualitative, not quantitative bars, just to give you an idea. And this means I'm producing way more, I need significantly more hardware. Or what I can do, instead, I can keep my small lattice size, and I can try to reduce the physical noise. And that ultimately means cooling down further and further. And this will have some other cost. And so the goal of this project is trying to find the balance between cryogenic load and resource state overhead. Before I get to the result itself, I'll give a little more context based off of the platform that I don't think everyone will be familiar with. So fusion-based quantum computing is in the title. I've not explained it yet. It's a giant stabilizer code where topological redundancy in the stabilizers is how fault tolerance emerges. And computation, so these entangling operations, they are called fusions, hence the name. And they're implemented through Bell-type measurements, and they're inherently probabilistic with linear optics. So what I want to do, I am using dual rail encoding. So each of these wires, the laser pointer is this one. Each of these wires is one mode, and we say if a photon is here, it's in qubit 0. If it's here, it's qubit 1. And if we send it through this pair of interferometers, if we send the psi plus and psi minus state, we see perfectly distinguishable detector patterns. But if you send in phi plus and phi minus, they have the exact same detector patterns. So we cannot resolve. We lose half of the information. So if we get one of these measurements, we always know the ZZ stabilizers, but we lose the XX parity. So about a quarter of the information is lost. That being said, even though I said you need to build redundancy to fight this non-determinate or this probabilistic effect, this is still too bad to actually do fault-tolerant quantum computing with. So what we do is introduce something called boosting. And this is just a more complicated circuit with auxiliary photons. And this reduces the amount of information lost. Instead of now 25% of the time you're losing the XX stabilizer, you're losing it, instead of 50%, you're losing it 25% of the time. And with this construction, you can now do fault-tolerant quantum computing, in principle, if you have no other sources of noise. I've also thrown around resource state a few times without really describing it pictorially. It's a graph state up to some Hamiltonians with 24 qubits in total. And these branches are kind of an encoded version of the 6 ring, basically providing even more redundancy. And to make one of these states with deterministic single photon sources, you need to start with 96 single photons, again, because everything is probabilistic and we're basically just heralding off of success. We do 72 photon subtractions. This is heralding off of a single photon click, and we'll do 6 of those fusion measurements on the way. And what we get, conditioned on everything being successful, is something that looks like this. So I showed this table at the very beginning. There's a bunch of ways to make these state. We're using deterministic single photon sources because this is the most modern technology. These other technologies exist, but they're not mature yet. So in the noiseless limit, to actually make this case, we need about 100,000 photons, which in the world of photons is not so many. I put an asterisk here because there's an assumption that we can do a lot of conditional multiplexing. If you try to do everything in parallel and just rely on everything succeeding, I did a back of the envelope computation. It would require about 2 to the 100 photons, which is too many. That's in the noiseless limit. We do consider the two sources of noise, which is optical loss. This is purely meaning whenever a photon interacts with a beam splitter or a detector, there's a chance of it just being erased. And so on this threshold graph, this affects purely the erasure probability. The more malicious type of noise is photon distinguishability. And so this is when there's a mismatch of modes, and instead of the qubits interacting in some sort of quantum interference, what you get is classical mixing. And so you just remove, you can't do quantum computing without quantum effects. And so this has a lot of detriments. It increases your error rate. It also increases your erasure rate. And it can leak you out of the computational subspace. So there's just a lot of nuance to it. Right, so next I want to present the results, but I want to start with a caveat that this is ongoing research and the results are preliminary. Most of the results are obtained through Monte Carlo simulation that is taken, or it takes days to actually get results. So to compute the logical error rate, we start with some tuple. We put in some sort of temperature and loss from which we compute distinguishability. And we can do some analytical result for roughly where we expect to rely on the threshold regime. We can stay roughly within 5 Kelvin. And then this is purely to give us an idea of how tolerant we can be to noise. And then we run it through STIM, which was mentioned this morning, for each tuple. And we compute the number of logical errors over number of shots to get some sort of idea of an erasure rate. And so here we can see that around 5 Kelvin, which is a little shy of our analysis, we break out of the threshold. This just means that now, even at higher, when we scale up the code distance, sorry, I should reframe. We're also changing the code distance, so increasing the lattice size. At some threshold, the more noise, the higher the code distance, the more noise we get. So we need to be within some threshold region. And from there, after getting enough data points, we can fit all of the raw data to some sort of model. Now, this model is very jagged because right now, sorry, our data is very sparse. In the future, it will be more full, but we can still see some general trends that temperature is much more impactful than loss, purely because of the fact that distinguishability adds to both errors and erasure. And on this threshold graph, I've not put axes yet, but the error rate is 1%, the erasure rate is 12%. To give some intuition why, is that your decoder knows when an erasure happens and knows that something went wrong. Your decoder does not know an error happened. And so you can withstand many more errors than or erasures and errors, and distinguishability or temperature is what leads to errors. For the cost, the resource part, I throw back to what Ariane talked this morning. We're mostly looking at the amount of power it takes to, or the amount of energy it uses to, we use in a cryostat. And so there's some sort of static overhead owing to laser, memory, demultiplexers, other components. This is on the order of kilowatts. There's some cryostat power that does depend on temperature. From 2, I think it's maybe 4 or 5 kilowatts. Around 6, it's 1 or 2 kilowatts. We're using the hardware specs of Quandela. So this is a very low Carnot efficiency 18 detectors per cryostat, and an emission rate of 1 gigahertz. And to get the total energetic cost, we just look at this plot, and then we multiply it by how many photons we need. Okay. So putting these things together, looking at both, trying to optimize the metric, the code, the logical error rate while minimizing the code distance. What do we see? We put it together, and we got some first look at the curves, and these are isometric, very scraggly curves. This is because of very sparse code data collection right now. Earlier I said there was some sort of maybe trade-off between code distance and temperature. The winner is clearly temperature. Like the best, for this model, for this primitive model, the best thing to do is to minimize the temperature, which minimizes the code distance, thus minimizing the number of cryostats you need. There could be more mature models in the future. Like we are making some assumptions of what we can do for free that might not be the case, especially with the serializing that we're doing. But that's for slightly future work. Yeah, so to summarize, there were two options. This is the clear winner with what we see right now. This could change in the future. We'll address the resource costs, but yeah, it seems to be that colder cryostat is more energy efficient than expanding your code distance. To quickly summarize, what we're doing is developing a full stack energetic framework for logical state creation for fusion-based quantum computing. And we've connected the black box, which is photon photon quantum dot noise model, to the macroscopic effects of logical error rate and resource cost. And then within the present model, the best thing to do is just reduce to cool down your cryostat as cold as possible. There's a lot of perspectives that we want to tackle before we even think about submitting. So this was a single, beyond just the more thorough resource analysis. I mentioned boosting. You can keep boosting further and further to reduce this non-deterministic effect. And so what we would like to do is extend this maybe one more layer. Beyond this, it's a little hard to derive phenomenological models. And we would also like to explore some of these other richer options. The Rust is something that is near term. Caterpillar would likely be more exploratory, but it would still be interesting to see. With that, again, I would like to thank all of my collaborators and also the organizer of QEI for putting on such a nice conference.
Okay, any questions?
Very interesting. Thanks, Nathan. I've got one question about the process of FBQC. Have you got any idea about the weight of the cost of generating the resource state compared to the rest? I mean, the fusions and then the measurements and the routing. I mean, about cyclotron architecture, of course.
Something that we've not factored in, this is a good question, and that I think will further exacerbate this notion. I think this might always be true, is that the overhead of the classical decoding for extremely large code distances would be enormous. Mm-hmm. We're not sure how to factor this in just yet, but it was kind of pinpointed out this morning in Michael Vassner's talk, like even the distance to code was this fairly large machine. So we would like to add these in, it's just not exactly sure how to do this in a fair comparative way.
Yeah, but what I meant also is the rest of the photonic process beyond RSG.
A lot of this is within, it's kind of hidden in...
It's hidden in some of the charts?
It is hidden in this plot, not all of this, but the linear optics and the detectors, it is within this resource cost.
Yeah, so it means that if companies like Psychotron were using a more efficient resource, photonic resource, single photon source, they would increase significantly their energy efficiency or not?
Yes and no. Not necessarily. So something that would immediately play a big reduction in cost is just having larger cryostats. So in the ones that Ariane was talking about this morning were for tens of photons, and so they're not very large. Cryostats do actually get more efficient once they're larger. It's like the square cube law. And so bumping this up to 10%, 20%, you do see a reduction in cost. And you also see a reduction, it's more temperature independent.
So this Carnot efficiency is for 4K, not 2K.
Yes, also, yes, it is. It would
those guys,
scale.
they need 2K, at least for the detectors.
Yeah, so this is a very primitive model. We basically plugged in the boson sampling model and adapted it to here. As I said, there's a little bit of wiggle room that we'll have to massage, but it is a good first estimate idea. And this would be a loose operating regime, as the sources and detectors need to be below 7 Kelvin. And then after this, you kind of have to change the way you're doing your cooling.
Any other question? Because otherwise I have one. So if you go to this exploratory slide. Yes, yes. So here you see this flattening with respect to temperature around 2.25 Kelvin. Why is that, and why that temperature? Is this something depending on the noise model or the generation of the photons?
It's likely the sparsity of the data collection, and the noise of the data collection. So this was done through Monte Carlo simulation, and purely from how error bars propagate, the less noisy the inputs are, the bigger the error bars are. Because when you take the log of the error, you get 1 over basically number of errors. And so you have this kind of blow up. And so I expect it would decrease a little bit, but the slope will decrease.
Okay, thank you very much.
I think the distinguishability as a function of temperature kind of scales exponentially. So here it's like 10 to the minus 7. And then it gradually grows to 10 to the minus 3 or something like this. And so there's less variation.
Okay, that explains. If there are no other questions, let's thank Nathan again. And the next speaker, yes.